Hello, my name is Stanford Gibson. I am the Sediment Transport Specialist at HEC, and I'm going to talk to you today about the new non-Newtonian mud and debris flow capabilities in HEC RAS. These methods were developed in coordination with our sister lab down at ERDIC, the Coastal and Hydraulics Lab, under the leadership of Ian Floyd, and Alex Sanchez, also a sediment specialist at HEC, added these to the 2D model and has done a lot of the work that I'll show you today. So this is a post-wildfire session. I don't need to make the case about how important post-wildfire analysis is, but in early January 2018, there was an intense rainfall event in the mountains up gradient from Santa Barbara, which happened to be on fire. A large-scale fire had swept through the area. It wasn't even completely out yet. The rain put it out, but it also mobilized a bunch of mud and debris that flowed down into Santa Barbara. There were 23 deaths and over $200 million worth of damage. This is kind of a headliner event, but we're seeing these events all over. And as wildfire areas are increasing, kind of year to year, this is becoming a much more important problem for us to tackle. And so one of the issues is that anytime that you want to do a flood analysis, a lot of folks are really interested in doing it in HEC RAS. HEC RAS is one of the most popular water resource softwares in the world. It's kind of the go-to software for a lot of agency and private sector analysts who do flood inundation modeling. We have over 100,000 users and have been downloaded in over 200 countries. And so it's really important to have the capability to do these sorts of analyses in this tool that lots of people know and want to use for flood damage analysis. But here's the problem. This is the Santa Barbara system. And so what you're looking at here is the blue lines are the inundation boundaries that the USGS went and measured. And it's easy to capture inundation boundaries from mud and debris flow because it leaves a debris footprint. And so these are pretty accurate inundation boundaries of what happened in this event. And so I'm just going to show you the results for this middle watershed here, San Ysidro. We went in and we built a 2D mesh of this system, and we just modeled it with the clear water flow in HEC RAS, and this is the result. And so what you can see is that's not very good. HEC RAS in clear water Newtonian mode didn't perform well, didn't reproduce the damage of this event very well. And so that underlines the importance of simulating these events with non-Newtonian physics. And so what I'm going to do is I'm just going to give you the very briefest overview I can of non-Newtonian physics and what we're actually trying to compute. And then I'll show you some laboratory validation tests, and then we'll go back to that field application and say, well, how does this work? How did this work out in Santa Barbara? All right, so first, let's talk about the approach taken in Debris Lab and in HEC RAS. And so here's the basic idea, is that most alluvial flows that we deal with, they carry sediment. That's why I have a job, right? And these sediment flows can be really high, right? Like a dam removal can have really high sediment loads. A reservoir flush can introduce a lot of sediment into the river. But even with those, what we would consider extreme events, the volumetric concentration of sediment in the water is still generally low enough that the particles don't interact meaningfully. But what happens as you add more and more sediment or solids to the flow is that those solid phase particles start to interact. And those particle interactions could introduce momentum and energy losses to the fluid to the point that it becomes significant to try to model what's going on. And so, as you start adding concentration, from lower to higher concentration, you get enough sediment in there that you start to get some viscous effects, and then eventually you get enough solids in there that the turbulence, it introduces turbulence losses, but then finally you get to high enough concentrations that the solid phase particles start colliding, and you start losing energy and momentum in those collisions until you get to the point where you have enough solids that you're no longer colliding, but you actually have friction between the particles, and then you start to transition from kind of a fluid to more of a like wet geotechnical solid, and geotechnical equations start to become more appropriate. And so this happens on a concentration scale, but you can't actually go in and put firm concentration breaks here because it also happens on a gradation scale. Finer sediment tends to be more towards the viscous forces, where coarser sediment tends to be more towards the stronger interaction forces. And so these two interact, and it becomes a little bit of a complicated proposition to identify what sort of material it is. Okay, so in a classic clear water flow Newtonian situation, most of our energy and momentum losses are at the boundary. And so we use the n value to compute those momentum losses, and it's all this kind of friction loss at the boundary. But as you start adding these interactions, these particle interactions, we start to get internal losses from each of these different processes. And so what we're going to try to do is quantify those internal losses. And so we're going to try to stick them into the St. Venant equations. Now don't get scared about these equations. This is actually very simple mathematically. These are the St. Venant equations. These are what we solve in unsteady flow. The shallow water flow equations in 2D are not the same, but they're similar, and the concept is similar. And so the way that we account for boundary friction loss in the shallow water flow equations is we include a friction slope, a dimensionless friction slope in the conservation of momentum equation. All we're going to do is add another slope, an internal loss slope, into the same term of the conservation momentum equation. And this internal loss slope is going to account for these other processes. Now, how are we going to compute that internal loss slope? Well, let me answer that question with a question. What is the equation for shear stress? Well, the equation for shear stress is gamma RS. And what's the S? Well, the S is the friction slope. And so this is kind of where the magic happens, because you can solve for the friction slope and cast the friction slope in terms of the shear stress. Or, in this case, you can cast the internal loss slope in terms of some sort of internal loss shear stress. And that's where the really powerful step is taken, because as soon as you define losses in terms of shear stress, we can start to leverage stress-strain models for different materials. And stress-strain models for different materials are what we call rheological models. Rheological models are models of how a particular kind of material deforms under stress. And so the simplest stress-strain model is what we call the Newtonian model. And it's what most of us use when we do any sort of hydraulic analysis. And that's this gray line here. And the idea is that, water under any minuscule amount of stress will strain, it'll deform, right? There's no stress under which water won't deform, and it deforms linearly. As you apply stress, you get a linear amount of strain. But not all materials behave like that. And so, the simplest alternate rheological model is what we call the Bingham plastic. The Bingham plastic also has a linear stress-strain ratio. The slope of that stress-strain ratio is actually the viscosity of the material, and so it'll be different than water. It'll be higher than water for, say, a mud flow. And it has a non-zero intercept, which means there's a certain amount of stress you can apply to this material before it will strain or deform at all. And that's really important for these mud and debris flows, because a mud and debris flow will eventually run out. Like water will just flow until it reaches the ocean or some depression, but mud and debris flows will eventually run out on a slope because the internal strength of the material is higher than the stress that's being applied. So it'll just stop, and the model has to be able to account for that. Now, there are also nonlinear stress-strain relationships, which we also have in Debris Lib and in HEC RAS, which we won't get to in this presentation, but they're there. So the idea here is as we kind of move through this taxonomy of high concentration flows, we apply different non-Newtonian models depending on the material type that we're trying to simulate. So then, using these rheological models, we compute a shear stress given the strain, and we plug it back in to here, get our internal loss slope, and boom, we're ready to go. We have the losses quantified in the St. Venant equations. Okay, so that's all we're doing. So the question is, does it work? Okay, using rheological models to simulate non-Newtonian flows is not the only way to do it. It's kind of the simplest way to do it. And so the question is, does it work? And so we've tested this against a wide variety of laboratory and mesoscale experiments. Let me just show you a couple of the ones that we've done. This is a data set from Parsons et al. Essentially what they did is they took a half pipe. They took a just regular pipe and cut it in half, and they just sent a number of very high concentration, like higher than 70% concentration of solids by volume, down this pipe, and then they measured the velocity of the front. And they did it, one of the cool things is they did it with a wide range of materials, like different concentrations, mainly different grain sizes. They had some fine materials, some really coarse sands. And they looked at just how these different things affected the velocity of these fluids. And so we simulated this we created a one-dimensional half pipe and then converted that to a two-dimensional terrain. In order to capture the resolution of that half pipe, I went down to a millimeter resolution in my two-dimensional RAS terrain, which I don't know if it's the world record, but I'm pretty proud of it. Then we simulated 8 to 10 of these different experiments with a wide range of materials and looked at how RAS and debris lib simulated them both with the Newtonian assumptions and with several different non-Newtonian closures. And so here's just one result. What we have is this is the whole half pipe, and here is just clear water flow. This is how clear water flow responded for the same flow rate. Here is the just the Bingham plastic result, and you can see that it hasn't gotten nearly as far. The stage is higher, the velocity is lower. And so how does this compare to reality? Well, this is the Newtonian solution on top and the non-Newtonian solution on the bottom. And you can see that we're not only getting the velocity right, but we're also like simulating the shape of this front as well. And so, that's kind of anecdotal. Let me show you how it looks across the simulations. And so on the bottom here, we have the observed plug velocity, the velocity of the front, and then we have what HEC RAS computes as the plug velocity. And up here we have the Newtonian solutions, which are all too high, but also if you just use continuity, also the stage is too low, and so this is going to misrepresent the potential destructiveness of these events. And then on the bottom, these down here, these are just with the Bingham plastic solution. And so you can see that the Bingham plastic solution is bringing the computed and the observed much closer together. We also looked at what this did to the lateral velocity distribution. One of the things that Parsons et al. Did is they measured the lateral velocity distribution across their flume. And so we wrote some code to get those data from RAS. And for these two experiments, we compared the observed to the computed lateral velocity, and the model's performing really well in that kind of two-dimensional arena as well, as long as you use good turbulence closures. That was one of the findings there. And so we've got these findings in a paper. The paper's in revision with Earth surface process and landforms. And we did it with multiple of these rheological models that we have in debris lib. But kind of one of the nice things, if you let's say maybe you're one of the most of the people who don't really love reading journal papers, what we did was we actually developed a multimedia method of materials. So basically we went through the whole process of creating this flume from scratch and then adding the non-Newtonian parameters in a 3-video series that are attached to the paper but will also live on our website. And so you can actually go in and walk through the process of building this model and adding the non-Newtonian parameters to the simulation to follow along. Okay, so then we also did an analytical analysis. This is the Hunger analytical model, and the Hunger analytical model says, hey, we have a 30-meter impoundment of high concentration material. We're going to let that run out and kind of see where should it end. Where should be the end of this front? Where should essentially the internal strength of the material is stronger than the shear stress, and so it'll just stop. And so they computed how far that should be. And this is RAS. We have the analytical result and RAS's computed result. We're modeling the front and the run out pretty precisely. But one of the cool things about the way that we did this is that we didn't actually add these to RAS. We collaborated with Ian Floyd and the folks down at ERDIC, the R&D lab in Vicksburg, Mississippi. And we developed a joint library of non-Newtonian algorithms. And this library is called debris lib. And basically all of the core software are calling debris lib. And so we've developed these algorithms together. We've V&V'd them and QA and QC'd them together. And we continue to add new ones together. And so as the library grows, the capabilities of all the models grow. And one of the cool things about this is that these models are very different. You know, ADH, Adaptive Hydraulics, which is the Coastal and Hydraulics Lab's 2D model, they're a 2D finite area adaptive mesh C++ code, whereas RAS is a 1D finite difference, 2D finite volume subgrid bathymetry Fortran code. And both of them can use these same algorithms. And you can see that they simulated the hunger model as well and got very similar results. And so this is part of the power of getting these in a library, and this library is available for other models. Okay, so then kind of the gold standard for validation tests for non-Newtonian models is the USGS Volcanic Laboratory Debris Flow Lab that's in the Pacific Northwest. Dr. Iverson and that team did just a number of these remarkable studies where they released these very high concentration, very coarse material down these very steep slopes at kind of a mesoscale. And so we applied, again, both of these models to this. You can see I developed it, again, in 1D and RAS and then converted it to a 2D terrain. What you can see is they measured both the stage and the arrival time of the front at different locations along the flume. And you can see that here we have the measured and the computed result in RAS for one of these simulations. And not only are we getting the arrival time and the stage right, is we're also capturing the shape of the flume in the runout pad. And if you can imagine trying to capture the shape of this runout with Newtonian assumptions, it's not going to hold that shape. With Newtonian assumptions, it'll just run out and fill the pad. Here, it runs out until it runs out of energy, until the internal shear strength is larger than the shear stress being applied, and then it stops. And it creates a lobe similar to what they were seeing in the field. Okay, so let me just wrap up by revisiting Santa Barbara. All right, so we took this model and applied it to Santa Barbara. And just to remind you of what we were getting with clear water flows. So what we did is we just added sediment to this. We kind of backed out the volumetric concentration from the USGS calculations. And we just used the Bingham model with the default parameters for standard soil used by O'Brien in Julian's textbook. And this is the result we got. You can see that now we are actually getting something that looks very much like the observed flood inundation boundary. And we did this actually with multiple watersheds, both San Ysidro and Mendocino, and actually each of these watersheds. And the non-Newtonian model did an excellent job of capturing the measured inundation boundary for the actual event. All right, so this work was funded by the Flood and Coastal R&D Unit of the U.S. Army Corps of Engineers, and it's under the leadership of the principal investigator Ian Floyd, who's really been the point guard for the non-Newtonian work in the Corps of Engineers. Alex Sanchez did a lot of the 2D coding and modeling that you saw today, and this will be in HEC RAS version 6.0. I'll just anticipate the first question. When is that coming out? The beta version will be out imminently. And so thank you for your attention. I'm happy to take questions.